right, so I think we are now live. So hello everyone, welcome back to another edition of Quarantine Thermo. Today we're very pleased to welcome Professor Janet Anders from the University of Exeter, who you see before you. So Janet, I guess, needs very little introduction. She's a leader in our field, expert in quantum thermodynamics. She was one of the kind of head honchos behind the COST network, which is probably the reason why I'm sitting here. It certainly got many of us into this field and was kind of instrumental in starting the whole thing. So thank you very much for that, Janet. So Janet's going to continue in the theme of strong coupling thermodynamics. Before I hand over to her, I'll just make a couple of brief announcements. So first of all, I mean, in terms of schedule for the rest of July, we will be continuing, but we sort of the schedule is going to change slightly, so we're going to be sort of fluctuating between 1 and 2 talks per week as appropriate for a sort of stochastic thermo community. So and then in August we'll probably take a break because I certainly need a holiday, and I think many of you probably do too. We were just talking about that with Janet. So yeah, but there'll be more announcements about that in due course, just to let you know, kind of watch this space. And then, yeah, as always, I'll just say that the format, as always, is so Janet's going to speak uninterrupted for as long as she wants, and then we'll have questions at the end. So if you have any questions, please just write them in the YouTube chat window, and I'll relay them to Janet at the end of the talk, where we'll have a kind of question and answer session. And please just make sure your name is kind of clear from your question if it's not clear from your username. So without further ado, I'll hand over to Janet. So I'll move myself out of the way, and you can go ahead and share your screen.
Okay, I'll share the screen now. Here we go. Some button to press. Right, can you see this? Okay, good. Then I'm ready to go. Yeah, okay. Thank you very much, Mark, and thanks to everyone else out there. Mark, thank you for organizing this. This, I think, is really a lifeline for the community, and I'm really enjoying the talks when I have a chance to listen to them. So today, I'm going to try and entertain you with some strong coupling thermodynamics. So firstly, I'm based at the University of Exeter in the UK, and recently I also started a part-time appointment in the University of Potsdam. But today I'm going to talk about some work done in my group at the University of Exeter together with Tom Philbin and Harry Miller. Okay, so the title of the talk is Thermodynamics Beyond the Weak Coupling Limit, and a particular aspect that I will focus on today will be the energy-temperature uncertainty relation that generalizes Bohr's uncertainty relation to the strong coupling regime. So let me start. Wait, this didn't work. Here. So there will be quite a bit of formula and technical things during the talk. So let me start with telling you the takeaway messages first. So firstly, if you're not used to strong coupling thermodynamics, then the main message maybe for you to take away is that it is possible to include a system's coupling to environmental degrees of freedom in a generalized thermodynamic framework. Some of those aspects we're going to discuss today, but there's much more already known, and there's also a lot more to be found out about how to include strong coupling into thermodynamics. What I'm going to talk today, firstly, is that in this framework, the system's effective Hamiltonian, which is going to be called HS star, which is the mean force Hamiltonian, depends on the strength of the coupling and also on temperature, and that is of course something that is not usual in thermodynamics, and that has some funny implications that I will also discuss later. Right, the second part of the talk will really talk about the quantum regime and discuss another energy operator ES that includes strong coupling corrections, and that energy operator and the system's equilibrium state, they may not commute. And this brings up some interesting features that have to do with coherences. And in particular, we are going to talk about a thermodynamic uncertainty relation, which is completely general. It is for temperature and energy. It's valid for classical and quantum systems. And it's also valid, of course, for weak and strongly coupled systems. And this is going to be the relation that we're going to see later. Okay, so let me start. The outline of the talk is this. We'll talk about first the introduction of what is actually this Hamiltonian of mean force. and also this effective energy operator ES. Yes, there are two. It is confusing. And then secondly, we will talk about thermal energies of quantum oscillators, and then the energy uncertainty, temperature and uncertainty relation. Okay, so let me start with the introduction. So what you normally basically in undergraduate physics have learned is the following picture. So you might have a reservoir with Hamiltonian HR over here, and actually that's never talked about. And then you have your system here with a Hamiltonian HS. And what happens is that your reservoir is initially in some equilibrium state at temperature beta, that's the inverse temperature here. And then what you do is you put your system into contact with the reservoir, and the contact is weak. It's just enough to make your system equilibrate with the reservoir. And what comes out of that actually is that when the system is much smaller than the reservoir, so for example, you can think of a cup of coffee that is standing in a big, big room. And what happens then is that the system and reservoir equilibrate to a global thermal state. So that's only true if the system is much smaller than the reservoir. So that's not true, for example, if you think of the system as a qubit and the reservoir as a qubit, that will not work. But obviously it works when you have a very small system, such as one harmonic oscillator that is coupled to many, 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 infinitely many oscillators. Then this is a very large reservoir. Okay, so what happens then is that your global state of the system and the reservoir becomes the thermal equilibrium state here. And this one has a temperature, of course, the inverse temperature. And now this is our starting state. And then what we normally do in standard textbook thermodynamics is we make a recoupling approximation, which we don't normally actually talk about. But the approximation is that the interaction between the system and the environment here is actually really weak. So it can be neglected in comparison to even the system Hamiltonian. And so what that means is that in the global thermal state here, we can drop this Vn term and we just get something like this, which of course splits into a product of two thermal states. So this is indeed our experience of macroscopic thermodynamics. We think of the system and the reservoir each in a thermal state in equilibrium with each other. Okay, so this is what we normally talk about in thermodynamics, standard thermodynamics. The system state, and it's the Gibbs state with respect to what I call the bare Hamiltonian HS. Now the problem is that this is not true for general coupling strength Vn. So when Vn is no longer small in comparison to Hs, but maybe Vn and Hs are somehow of the same order, or Vn can even be larger than Hs, then we have to start thinking about how that will change thermodynamics. So for a start, if you think of the global thermal state here, this one, and we take the trace over the reservoir, then that would be our reduced state of the system. And as you can easily see, when Vn is there, that obviously is not going to be equal to the Gibbs state for the bare Hamiltonian. So our system state in this global thermal state is not actually a Gibbs state anymore. And this happens particularly when the Vn is not small in comparison to Hs, and that happens when our system is small. So when the system is small, basically you can think of it as the surface area where the interaction happens is then comparable to the volume, which is like Hs. So for small systems, the competition between the own bare Hamiltonian and the interaction is really, really important. So that's why this comes up for us within the context of stochastic thermodynamics and quantum thermodynamics. Okay, so what one can do is that, so we have a well-defined reduced state, rho s, of our system. And what one can do now is one can define from that state a Hamiltonian here that's called Hs star, which is the effective Hamiltonian or Hamiltonian of mean force. And this is simply a definition. This is the thing for which this state becomes a Gibbs state. Now, this whole thing goes back to Kirkwood in the 1935. So he already discussed this in the classical context. And in fact, this Hamiltonian of mean force is really widely used in chemistry. But in our context, it's only recently that this has been discussed. So to summarize so far, we have a Gibbs state now with respect to a mean force Hamiltonian. And this mean force Hamiltonian is defined by this sort of combination of things. And the partition function here is a partition function for the system. that that you can see is the ratio between the full partition function of the global state for a system and reservoir and the reservoir alone in a thermal state. So the partition function of the system basically talks about the information that one has to take into account when you put the system into the reservoir that was already in equilibrium before. Now, one of the standard thermodynamic relations that you have learned also in undergraduate physics is this one here, which says that the average energy in the thermal state, which I've called pi, so this is the expectation value of the Hamiltonian, equals minus d beta log z. But now we have, right, okay, so what we're going to do is we're going to define U star as our new energy of the system. And we're going to define it as the thing that, that you get when you take the logarithm of Z star and differentiate it with respect to beta. And this is motivated by wanting that the total energy is extensive. So the reservoir and the system energy together add to the total energy. And so that links back to this ratio of the partition functions. So anyway, this is our new energy here. And what is now awkward is that because the HS star, as you can see from the definition here, HS star itself is a function of beta. So that is very awkward because standard thermodynamics assumes that beta and HS are completely different things. Now, our Hamiltonian has started to become temperature dependent. And for that reason, when you take the derivative here with respect to beta, you are not going to get trace of rho times H star. So in other words, our energy is not anymore the expectation value of HS star. But one can find that it is the expectation value of another operator, and that one I will call E, and this has been suggested by Seifert as one possible choice of an effective energy operator. And as you can see, E here is defined as a derivative of beta times HS stars, and so that comes from up here. Remember, the state now is a Gibbs state with respect to that. So this choice comes from identifying that part as the thing that actually matters when you calculate log z derivative. Okay, so we're going to have, therefore, the following picture. In the recoupling regime that you're familiar with, your state is a Gibbs state of the standard Hamiltonian, the bare Hamiltonian, and your energy, of course, is the expectation value, and there's this relation between the energy and the partition function. Now, in the strong coupling regime, we saw that our state becomes a Gibbs state with respect to the Hamiltonian of mean force, and that Hamiltonian of mean force in general will differ from the bare Hamiltonian. Our energy is still defined like this, but we need another effective energy operator, E, to be able to express this energy as an expectation value. So in other words, the role that was played by one Hamiltonian now is played by two different types of Hamiltonians or energy operators that both, of course, converge to HS in the limit of recoupling. Okay, now let me talk a little bit about thermal energies of quantum harmonic oscillators, just as an example of what this all does. So let me briefly explain the Hudna-Barnet model. Most of you might be familiar with the Caldera-Leggett model, which is for a discrete bath of harmonic oscillators. Here is the Hudna-Barnet model. It describes the harmonic oscillator coupled to a continuous bath of harmonic oscillators. So we're simply talking about a HS that looks like this, and an HR that looks like this, where here there is an integral over all frequencies. And the interaction is between the Q oscillator and the X oscillators of the bath here. And here's a coupling function, alpha omega, which tells us how strongly each of the bath operators couples to our actual operator, actual harmonic oscillator position operator. Okay, so now the total Hamiltonian, of course, is the sum of all of them. And what has been found before in this paper by Tom Philbin is that this total Hamiltonian here can be fully diagonalized under some constraints, and the constraints have to do with this susceptibility, having some imaginary part that is not too big. So the susceptibility is proportional to this coupling function squared over omega. So basically, the Hamiltonian can be diagonalized and is physical for certain choices of this coupling function. So now what you will remember, of course, from standard thermodynamics is that your bare Hamiltonian for the harmonic oscillator is this. And when you calculate the standard energy for that in a thermostat, you will get this type of expression, which in the limit for large temperatures, so the classical limit, of course, becomes kBt. So it's just twice kBt half for a harmonic oscillator. Now, for our strongly coupled oscillator, we can use the diagonalized H total and evaluate this partition function thing. And then we can take the derivative with respect to this, to beta. And then we can get the oscillator energy at strong coupling. Okay, and I just want to show you this funny expression, which says that at strong coupling, this energy of the harmonic oscillator is still, of course, a function of something to do with temperature, and there's also omega 0 in it, similar to here. But as you can see, the whole thing is much more complicated, and this is because there's a chi in there, and the chi, oh gosh, sorry, it's a phone going off. The chi is related to the coupling function. So basically the coupling function alpha is proportional to the square root of chi times omega. And so when alpha is 0, chi is 0, this will all vanish and this will simplify to this. But when chi is not 0, the whole expression will become different, and you can see that your energy will depend on the coupling. So it will be very different. So same thing, but now if we take the classical limit, so we assume that this cotangents can be approximated for high temperatures with this formula, then what turns out is that this entire expression that one gets there actually simplifies to kBt always. So for very general susceptibility, this is always true. You always get kBt. And so in other words, for the classical limit, the effect of coupling to the environment does not matter. You always get kBt. Maybe that's easy to understand, of course, because the frequency dependence was only even in the quantum energy in the first place. But it is still interesting that the strong coupling doesn't affect the classical expression here. On this is, so if one wants to do perfect ohmic damping, one has to choose, in the quantum case, one actually has to choose a non-permissible susceptibility. So one that looks like this, which doesn't satisfy the condition that I stated earlier. And only with this susceptibility will one get the standard Langevin equation. So the standard ohmic damping that one often wants to use would be this. So, but the point is that this is only possible for susceptibility that is actually not physical. And when one inserts that into the formula here for the energy, then one gets this expression, which doesn't matter that much, but the main point is this expression diverges for any temperature. So in other words, if one wants to do perfect ohmic damping, that's not going to be possible because it requires infinite amount of energy. So it's actually non-physical in the quantum case. Obviously, when one has only approximate ohmic damping, that's fine. Okay, so the summary for the first part is the exact ohmic damping that is often used is physical for classical oscillators, but not actually for quantum oscillators. So one has to look out for that a little bit. The mean force energy US star of a classical oscillator is always kBt, independent of the coupling to the reservoir. But in contrast, in the quantum case, for quantum oscillators, the mean force energy US star depends very much on the coupling function alpha, which gives you the chi. So that's basically the main point. And then more generally, as I explained now, there is this Hamiltonian of mean force, and there's also this other energy operator. And more generally, it is possible to include the systems coupling into to the environmental degrees of freedom in a generalized thermodynamic framework. So as I said, this goes back to Kirkwood, and then of course there's been a lot of work, but more recently within stochastic thermodynamics, maybe I can point out Jarzynski's paper where he extended his Jarzynski equality to the case of a strongly coupled system. and showed that indeed when you have a Hamiltonian for the system that is still controlled by some protocol, plus the environment which is left alone, plus the interaction which is also not changed in time, then one still obtains something like the same as a Jarzynski equality. The only thing that changes is that the delta F, the free energy change that we usually have here, is actually the free energy change according to the Hamiltonian of mean force, so not the bare Hamiltonian. So that is the impact of strong coupling, also in the context of fluctuation relations. That was a classical result. So a few years later, Campisi and Hängi and others, Togner and Hängi, they extended this to quantum systems. So same story. So when the Hamiltonian of the system alone changes, then you get the fluctuation relation. So again, in the Campisi, Togner, Hängi case, of course, they used a 2-point measurement on the entire system and bath to work out the work distribution, and then this is how you get also a fluctuation relation for the quantum case. Okay, then back on the classical side, a few years later, Seifert also showed that in the strong coupling case, you get an integral fluctuation relation for the entropy, so similar to what you know for recoupling thermodynamics. And he also proposed this energy operator that I already introduced earlier, which looks a bit different, but it's the same thing here. And then there have been many other papers. So in particular, there is Philipp Strasberg and Massimiliano Esposito's paper here that talks about classical entropy reduction, and also Harry Miller's paper here on fluctuation relations in this case. I should also mention that as Philip discussed last week, there's controversy about the uniqueness of the choices of the Hamiltonian of mean force, whether it's actually unique or not. And maybe I can point out that these papers here all discuss these aspects, and maybe you can have a look at Philip's talk also for further information about that. Yeah, finally, I'd like to point out here that while some of those are sort of general and somewhat abstract because they show general relations, this recent paper is very interesting because it talks about a specific example of a quantum dot that's coupled to an environment and works out the dynamics of the system, and also shows how the Hamiltonian of mean force steady state, so the Gibbs state, is basically achieved. And it discusses many very interesting features. In fact, I think, Mark, you are one of the authors of this paper, so I'm very keen to hear more about this. So if you do give a talk, this could be one of the topics you could talk about. Right. So so this sort of provides the context of where we are with the mean force Hamiltonian and strong coupling thermodynamics. So I'll come now to the second part, which is about the energy temperature uncertainty relation. So what Bohr actually, a long time ago, what Bohr postulated or sort of argued in a heuristic way is that there is an energy temperature uncertainty relation. So temperature as in inverse temperature beta times delta U is bigger than 1 for thermal state. So the delta U is fairly obvious, right? Delta U is the variance of the energy within a thermal state. So you have a distribution, you have a variance, that's clear. Beta is less clear what it might mean, because normally, of course, temperature arises as a Lagrange parameter when you derive the thermal distribution. And so it's just simply a single parameter, so it doesn't feel as if it has a variance. But this delta beta here is going to be about estimating temperature. So it will be about how well can you actually know the temperature or inverse temperature when you access a system and ask it the question, what is your temperature? So this is what Bohr said, this relation should hold. But again, this was valid for systems that are weakly coupled to an environment. So again, this interaction is not taken into account. And so we want to look at the correction of this inequality for systems that are strongly coupled to the environment. Okay, so let's recap. For strong coupling, we have this funny situation. So our energy uncertainty that is going to go into this inequality is going to be delta U star, and delta U star is going to be the variance of rho s of ES square traced with rho s and then minus this here squared. So it's this operator that is giving us the uncertainty. And now we come to the other bit, which is very interesting. So I need to introduce the Wigner-Yanase-Dyson skew information. So let's consider the uncertainty or variance of an observable A in a state rho. Here's the variance, and let's define it as actually rho times dA. Yeah, sorry, there might be a mistake here. And dA is the shifted one, so that dA is actually an operator that doesn't have a mean in the state rho. But the main point of this is that we want to separate a classical uncertainty. So if A and rho are diagonal in the same basis, then the uncertainty that can arise actually only arises from rho being mixed, right? This is the classical part of the uncertainty. And we're going to call this, maybe ignore the middle line here. So the variance is, we're going to call that K, that's the classical part. And the quantum part is if rho is pure, so it's a very quantum state, then the uncertainty arises whenever rho has coherences in the eigenbasis of A. So the variance of A and rho is going to be 0 if there are no coherences, but can be non-zero otherwise, and that would be a quantum contribution to the uncertainty. And so in general, one wants to partition the variance into these classical and quantum uncertainties. So like this, K plus Q, and Luhr set up certain criteria for this. Of course, we want K and Q to be positive quantities. They should measure uncertainty. And we want K to be 0 for pure states, and we want K to be concave, so it should increase under mixing. And what Luhr found is that this skew information that was introduced by Wigner-Yanase-Dyson in the 60s, that skew information is given here. It looks complicated. It's two commutators, this one here between A and rho to the power A, and this is another one commutator. And then you take the trace of the entire thing. And A is a parameter that can range from 0 to 1. So this is the skew information, and this skew information fulfills these properties where the variance is now well defined and Q is well defined, and K is then simply the difference between the two. Not only that skew information that I just introduced with the parameter A satisfies these conditions, also the average skew information where you simply take the integral over dA here from 0 to 1 also satisfies these conditions, as has been pointed out in these papers. So maybe you ask, okay, there seems to be also quite a bit of variability. So why am I just talking about this? What is interesting is that in the next slides, this average skew information will be a natural quantity that will come out from a thermodynamic investigation. And so that's why I wanted to introduce that. And it is unclear, for example, why this is one of the many open questions in this field. Why is it this particular Q and not one of the other ones here, or indeed any other thing that fulfills the criteria that we discussed before, that appears in the thermodynamic context? This is not clear at all. But okay. So let's talk about temperature uncertainty then. So this temperature uncertainty, as I said, is going to be understood in the context of optimal parameter estimation. So if one considers all possible measurements or POVMs on a quantum system, the question is, what is the ultimate precision that we can hope for? And the general answer to this question, of course, is the Cramer-Rao bound that tells us that for a single shot measurement, the uncertainty in the parameter estimate theta is going to be bounded from below by 1 over the square root of the Fisher information. This is the quantum Fisher information. I won't state the definition here. This is a fairly old result. It's used a lot in estimation theory. But in our paper, what we showed is that for exponential states, so states of this form, rho theta with some operator A and some partition function here, one finds that the Fisher information can be bounded from above by this expression. So K is the classical uncertainty of this operator d theta A with respect to the state rho theta. And so hence this means that the uncertainty in the parameter is going to be bounded from below by this expression. So of course we want to use that for temperature estimation now. So we have states that look like that with a Hamiltonian of mean force. So we want to choose theta as being beta, and A theta up here is beta H star. And that means just plugging in the formula means that d beta, the uncertainty in temperature, is going to be bounded from below by, this expression here is actually our E. This is the derivative of beta times HS star. So this is actually the E operator, the energy operator. I won't go much further into quantum thermometry at this point, but if you are interested in estimating temperature and what the questions are, you might want to have a look at these papers here by De Pasquale and others, and Correa and others that discuss that in a recent context. How do I go? Yeah. Okay, so remember that we had a classical and a quantum part to the variance of our energy, and now we can simply plug that into this formula here, and what we then get is already the general temperature energy uncertainty relation. So what we find is delta beta is bigger or equal to 1 over square root, and this is the variance of the energy, and here it goes minus Q, so Q is this skew information, and of course Q is a positive thing. So obviously, if Q is 0, right, you can forget about this, and we simply get 1 over delta U star. Okay, this is the Bohr result. It tells us that delta beta times delta U is bigger than 1 in general. But if Q is actually positive, then of course this expression down here is going to be smaller, which means that the uncertainty is actually going to be larger. So this is going to mean that the quantum part, so what it means is that the uncertainty in the temperature consists of 2 parts. It consists of the thermal energy uncertainty, and then this here is going to be like a plus, if you bring it up, plus a quantum uncertainty that comes from the state rho and the energy operator E not being diagonal in the same basis. Okay, this sounds really odd. So let me give you an example. So let's work with the discrete Caldera-Leggett model, the old one by Grabert and others, done in the 80s. So again, we're talking about a harmonic oscillator, this time with a mass. We have a reservoir, we have coupling, and we have a specific spectrum here that we've put here. And if one works out from this, the Hamiltonian of mean force, then of course we're still going to have a harmonic oscillator for our harmonic oscillator. The thing that has changed are the parameters of the harmonic oscillator. So the mass and the frequency will become temperature dependent as a function of the coupling to the bath. With also a function of the coupling to the bath. And now one can also take the derivative with respect to beta of beta times H star. And what one gets here is that you get something that is proportional to H star, but also a term that is different. So you, of course, this can also be diagonalized in ladder operators, and then the ladder operators themselves are temperature dependent. And this gives rise to this term here that has ladder operator squares. And as you can see, this is not going to commute with HS star itself. So the bottom line of this is that ES, this energy operator, does not commute with HS star, the other Hamiltonian, the mean force Hamiltonian of the system. And what that means is, so yeah, for our example, the 2 operators don't commute. And what that means for us is that this skew information, remember, in our context, we want to have the skew information of ES in the state rho S. So we want to put that in here, but rho is our state of the system, which is, by definition, the Gibbs state of the Hamiltonian of mean force. And the point is that HS star and E do not commute. So these commutators here won't be 0. And in fact, this is a picture of the skew information as a function of temperature and also as a function of the coupling strength of the harmonic oscillator. So you can see Q is clearly not 0. And what that does is again, this is the uncertainty relation. So the uncertainty will become larger when there is coherences of rho in the energy basis of ES. Okay. Right, so I'm coming towards the end. So the last part I want to discuss is the heat capacity. This is just a short comment. So in the recoupling limit, the heat capacity, C, is defined as the variation of the energy with respect to temperature. And in the recoupling limit, this turns out to be the variance of the energy with temperature. The variance of the energy divided by temperature. Right. So now we can evaluate this too using the effective energy operator results in our general expression. And so what we get is the heat capacity is given by this first term, which is the standard term. But then there are two additional terms here. So this one here is again the skew information. This is a quantum correction term that only occurs when our state rho has coherences with respect to that energy operator E. And then there's another term, which is a classical correction term that arises from the temperature dependence of this operator E. And the last two terms, at least in principle, could make the C negative, which is really awkward. And this has been discussed by Henke and Torkner and Ingwald in these papers here. Yeah, so this is an interesting feature that might occur, but I have not really looked into negative heat capacities at this point. So let's just look at the heat capacity of our harmonic oscillator. So this is a graph of the harmonic oscillator that shows the heat capacity, C, as a function of temperature and coupling strength. So the usual recoupling thermodynamics result is in the back where gamma is 0. So you would start with something that is, well, it starts with basically the cotangent hyperbolicus derivative, and then it goes up to k, so a constant k, right? But when the coupling gamma goes on, then you can see that the heat capacity is really affected by that. So it goes down in comparison, and the going down comes from the skew information being ramped up. So remember that was the skew information here as a function of coupling strength. So the larger the coupling, the more Q goes up, which means the less the heat capacity will be. So in other words, this really has significant effects. The strong coupling has significant effects that I expect should be measurable, and it would be very interesting to see those actually measured in experiments. Okay, so let me come to the summary. So what I've shown is that in the quantum regime, the energy operator ES, which includes strong coupling corrections, and the system's equilibrium state, which is this guy, may not commute. And this gives rise to the skew information, which looked like this for a harmonic oscillator. And we also looked at the thermodynamic uncertainty relation that exists for temperature and energy that contains strong coupling corrections. And in particular, the Q appears in here. And the uncertainty and temperature of a system will become larger when its equilibrium state is not diagonal in energy. So in other words, the quantum uncertainty really takes a role here. Maybe I should mention a couple of open questions. So I think what is actually really important is something that Jochen Gemmer pointed out 2 years ago, that we don't really have a good mathematical quantification of what we mean by recoupling. So when we say V int is smaller than HS and HR, we have an intuitive understanding of what that means, but we don't have a mathematical understanding of it. Because of course, these are operators, so it's not just any numbers that we're comparing, but we might have to take into account the occupation of different levels in those operators that we're comparing. And likewise for the strong coupling, what exactly does it mean when the interaction strength is comparable to HS? So these would be very nice to have some quantifications. Another aspect that is very, very important is the dynamical convergence to the local state. So this paper by Purkayasta and Mark and others, I think it discusses the dynamical convergence in a nice way. It expands to second order in the coupling, and it shows that the master equation basically leads to a local steady state that is given by the Hamiltonian of mean force. So it shows it very nicely for one example, but we do need more examples like this, because at the moment I can't really think of very many of them. And then thirdly, as I already mentioned, it would be very interesting to have some experimental methods of accessing information about the system's strong coupling and the thermodynamic corrections. So thinking of experimental realizations where one may be able to modify the coupling to the environment and see the impact of the changes as a function of the coupling would be very interesting. So that's also not done in, as far as I know. Okay, so with this, I would like to come to the end and just thank the people who I've worked with on this exciting new direction, which I think is really going to be important for the next couple of years, this strong coupling thermodynamics. The first part about the harmonic oscillator energies was with Tom Philbin, and the second part about the energy uncertainty relation was with Harry Miller, who's now at the University of Manchester. And also I should point out, Harry has written a very nice chapter for the Springer book on thermodynamics in the quantum regime, which deals with this Hamiltonian of mean force and introduces it, and also has a lot of references, so you might want to have a look at this if you're interested in this. I should also mention that I'm currently finishing a paper together with Simon Horsley on working on the Hudna Barnet model for spins, which is very interesting. And this should be on the archive soon, and I hope to be able to speak about this to you sometime soon, maybe even at the Quantum Thermodynamics conference in Barcelona. If we go there, or if we do this online, we will see what happens. Okay, with this, I would like to thank you all. Thank you.
Thank you very much, Janet. Super clear talk, really nice. So yeah, as always, we have time for questions. We've already had some questions, a question already. Actually, first, let me just say thank you so much for mentioning our work. It's really kind of you to point that out. So thank you. But yeah, so let's move on to the questions. So first question is from Andre Timpanaro, who is asking, do HS star and ES star depend only on the system and interaction Hamiltonians?
Yes, they do. When he says only, does that mean, what does he imply? I guess they also depend on temperature. So they do not only depend on HS and V int, the HS star will also depend, and E will also depend on temperature, both of them. To what degree they will depend on the bath, I don't know, because most baths are consisting of harmonic oscillators, and all you need from the bath is then something like that you will get a thermal average, such as a cotangent hyperbolicus, which comes from the bath being harmonic oscillators. If you change it to a spin bath, maybe that becomes different. I don't know.
Okay, cool. Thanks. Yeah, that's interesting. All right, so next question is from Gabriel Langi. He says, hi, Janet, thank you for the fantastic talk. Could you please comment on the optimal POVMs for obtaining the quantum Fisher information?
Yes. Yes, this is a good question. Yes, so this is, yeah, I don't know so much about this because I'm not an estimation theory person, but this is a huge topic, right? This is about, you can prove that the Fisher information gives you the right bound, but it doesn't necessarily tell you how you should choose your POVM to be able to get this bound value. So there is a discussion about this. In our case, for our example, we found the perfect POVM, but in general, I don't know the answer. I might have to ask Harry, or maybe Harry can comment on this. Yeah, there's other people who know estimation theory better than I do, who will be able to comment on the possibility of finding the optimal POVM that gives you the Fisher information.
So
it's a difficult question.
It's not just the measurement of ES star. I mean, I somehow would have assumed that it was a measurement of the energy operator. And because in weak coupling, that is the answer, right? That's the optimal POVM.
No. This is the problem. I mean, in very general terms, this could be anything. And in our case, I don't remember anymore what it was, but this is not a trivial question at all. So this is a difficult question. What would be and indeed that brings me to the thermometry papers again. You might want to have a look at those thermometry papers. Can you see my slide here?
No, you're not sharing screen anymore, I don't think.
Yes. Matt, let me just share this.
Sure.
You should be, yeah.
Yes.
Okay. Yeah, So these papers here, so basically this is the question of thermometry. So these papers might be the right ones to look up in the context of how to find the measurement, this POVM that will give you this bound. It's difficult.
Right.
Mm-hmm.
Okay, thanks very much. So then we have a question from SN Nazir who says, "Hi Janet, thanks for a great talk. A couple of questions. Okay, I'm going to assume these are different questions. So one, does a global Gibbs state well approximate the Barth state as well as the reduced system state?"
Does the global Gibbs state approximate the Barth state? Yes, because I mean, it's very hand wavy, but the assumption is that the reservoir is much, much bigger than the system, right? So the assumption, so in the weak coupling assumption, of course, we can make this assumption because V int is really small. But even in the general case, the point is simply that both V int and HS are both assumed to be really tiny in comparison to HR, because HR is the massive reservoir. So the hand wavy argument is simply that you can drop both of them when you look at the reservoir, and you don't have to take that into account. There's a lot of controversy about this, because of course it is a bit of it's a chicken and egg problem, right? What is a good reservoir? So the reservoir is good when this is satisfied, say I, but other people might say no, it should be the other way around. I'm not sure this answered the question.
Yeah, that's interesting. I probably have a different point of view on that as well, but I mean, because I mean, the reservoir can be strongly out of equilibrium, but it can still equilibrate the system, right? But far away from the system, things may be completely out of equilibrium, right? But you don't care anymore.
Yes. No, I have assumed here throughout the discussion, I've assumed the global thermostat. Mm-hmm. What is interesting is that when you, for example, when you take a master equation approach and you model your system as being in contact with an environment, and it may equilibrate locally to look something like a Gibbs state with respect to the Hamiltonian of mean force, that doesn't imply that the entire state of the system and the environment together is actually in the global thermostat. Right. If that makes sense.
Yes.
But
yes.
It can locally still look as if it was.
Yes. I that's how I interpreted Essen's question. Maybe I misunderstood something.
Yes.
But no.
Yes.
Anyway, thanks. That hopefully, yes. Thanks anyway. Thanks. Sorry for interrupting.
Just to say, so for this, for maybe in this context, what you really think of when you start with this global thermostat is that you have an additional universe that has equilibrated both your system and reservoir together into a global state. So them alone, they will not be able to equilibrate otherwise. Right.
Yeah. Okay, great. Thanks very much. Let's move on to the next question from Essen, who says, so question number 2 is, does the condition on when the continuum damped oscillator model is solvable have anything to do with a lack of counterterm in the Hamiltonian?
This is also a good question. I don't know the answer other than maybe, but I would defend that basically there are two schools. One of them says let's use a counterterm, and one of them that says let's not use a counterterm. So let me belong to the school that says let's not use a counterterm, because I find that reasonable. And then then this condition comes up as being a condition on you can diagonalize your Hamiltonian only under that condition. If you include the counterterm, I think one of the reasons why you include it is because otherwise your Hamiltonian might not become diagonal, might have infinitely large negative eigenvalues, which means it is not diagonalizable anymore. So this might be the reason why you included it in the first place. Does that make sense? So I haven't included it, therefore I have this condition.
Mm-hmm. Yeah, that's very interesting. Thanks. Okay, let's move to the next question from Karen Hovyanishan, who says, simplistic or just his own intuition suggests that Q should increase with beta. Yeah, I had the same question. Is it something you also observe or generically expect? Actually, it doesn't, right? It goes to 0 at low temperature. So I had the same question.
Yes, increase with beta, right? Yes, beta. Well, it does increase, right? I mean, so basically increasing with beta means going down this way. It does increase until a point, right? So it does, yeah. it does increase. So that I guess if you don't look, I mean, you can't see my hand, but basically, if you hold your hand over this graph on the left, then it clearly increases. Why it falls off at the end, I don't know. Obviously, it's because the state. It's because the state becomes pure, of course. Well, one has to go through the moves, but obviously the purity of the state is also going to matter.
I see. I mean, but does this imply at that zero temperature, ES and HS are essentially, they commute with each other? Is that, because I mean, HS shouldn't necessarily, I guess maybe it's not even defined at like zero temperature. So.
Yes, I have to look that up. I don't know anymore. Yes.
Okay. Okay, thanks. Maybe I'll move to the next question because I think we have lots of questions. Next question is from John Gould, who says, "Great talk, Janet. Thanks. I wanted to ask you to comment a bit more on if there are any good ways to experimentally measure fluctuation theorems in strong coupling. Do you have to assume that you can measure the bath? It seems very hard."
Oh, yes. Okay, I mean, experimentally, there's different parts of this question. So let's start with the theoretical side. I think the point is that in the quantum regime, then this brings us back to the Campisi paper that says you would have to project your entire system and bath in the full energy basis. And yes, I would say that this is not feasible at all. That's why I think any explanation of how one might at least approximate something by just doing measurements on the system alone is very interesting. But I am unsure whether that is so. This was a discussion we had last week with Philip, whether this is possible or not, and there were certain conjectures having been made, but Philip also showed some results, but I must say I'm not entirely sure now whether they were not classical. So I think he only showed, or I'm not sure now. But this is one thing. So basically what Philip talked about is local measurements. I have to reread the paper to be able to answer this correctly, but Philip's paper will potentially answer that question. I think the next question is about experimentally doing anything like that. This is a much harder question. So I think we need experiments, really simple experiments that first of all not even do any fluctuation theorems, which are in a way complicated. All we want is to show the effect of coupling on thermodynamic properties of the system itself, such as energy, heat capacity, things that are somewhat easy to measure. So we don't need fluctuation theorems to actually already have some insight into strong coupling, because at the moment I don't think we have any experiments that verify this theory really experimentally, even though it's becoming more and more of an established framework that makes complete sense, which is really great, but we don't have experiments that really measure properties that we are predicting. We need to work on that.
Okay, thanks very much. So the next question was from Angel Rivas. I think this is related to Essen's question, but so Angel says, "Thanks for the nice talk. I'm wondering whether the singularity of the ohmic damping is related to some kind of unboundedness from below in the total Hamiltonian."
Yes, that's exactly the same that we talked about. Yes.
Okay.
Yes, it has to do with that.
Mm-hmm. Right. Okay. Cool. So then the next question is from Susana Huelga, who says, is Davy's theorem not helpful in this context to characterize non-weak coupling?
Ooh, Davy's theorem. What does Davy's theorem say?
I actually don't know this, so maybe Susanna, if you can clarify in the comments, I can move to the next question maybe, and then we can get the clarification from Susanna, and then I'll ask the question. So the next question was from Franklin Luis dos Santos Rodriguez, who says, "Thanks again for the talk. This might be a silly question, but a local energy measurement on a strongly coupled system. So what would a local energy measurement on a strongly coupled system retrieve results from? Would it be the system Hamiltonian? Would it be HS star, ES?"
That's a very good question. I expect it to give US star, and so I would expect it to be a measurement in the energy, this ES operator here. But it all depends on how you're going to do the measurement. If you're really doing a quantum measurement, then yes, I guess. Yeah, then you would be projecting into those. So a lot of the literature that I've also covered is classical. So the whole thing is also the framework is also interesting for classical systems, and of course in a classical system you don't even have energy eigen states, right? You can get your energy by basically getting a kinetic term and a potential term. So the discussion changes a little bit in that case, because you could separately measure different aspects of energy and then combine them. But in the full quantum case, yes, you would be projecting onto the energy eigenstates of this ES.
I see. And this ES would be simultaneously measurable with the environment energy in principle. Is that right? Because it's additive with the environment energy, isn't that
Yes,
part of the...
it is
Okay.
additive, yes. Yeah, I don't personally think of measuring the environment, because the environments that I'm considering are massive.
Sure.
So, but this is not something that I can measure. But you're right that if one actually has this BAF engineering or BAF, the ability to measure the BAF, maybe calorimetrically, like Yucca-Pecola's group, then one is maybe able to access both parts of that equality. So the energy of the BAF and the energy of the system, yes, is also not been done, not been put together even theoretically, as far as I know.
Okay, thanks very much. Yeah, so Susanna had a clarification. So she says Davies bounds how fast the 2-time environmental correlation functions decay.
2 times correlation function decay. And what is the question?
So the question was, so is Davies' theorem not helpful in this context to characterize non-weak coupling? Because I guess, very fast decay of correlation functions is, of course, one of the crucial assumptions of the normal weak coupling limit.
I know what she's referring to. I think I believe she's referring to the questions I posted at the end. How to mathematically quantify weak coupling.
Yes, and Rivas also is clarifying, saying this is the question. Yeah, so
yeah, so I this may be true. Yes, but I guess yeah. But the BAF correlation function is going to be mostly a function of HR, isn't it? Where does the V int go into that?
Well, I think it would be a correlation function of, V int would definitely go into it, because it would really be V int. In some sense, it would be a correlation of V int with itself, but evolved under the BAF Hamiltonian somehow.
Yes. Okay.
Right?
Okay. Yes. Yeah. Okay. So she's suggesting comparing this one with something else. I guess HS, something with HS. Maybe. I don't know. Yeah, I guess. I don't know.
Okay. Susanna is saying that she's going to write to you with more details anyway. So I guess that's a discussion you guys can continue offline.
Yeah, I think the interesting thing about it, this has also to do with the second question about the convergence. This has to do with the fact that on the one hand side, what I talked about today was actually all static. Everything was static. I just simply assumed the global thermal state, and we did stuff on that. But of course, there is the convergence issue of dynamically going there, which we discussed already a little bit. And of course, the BAF correlation function is one aspect of that. And of course, if one talks dynamically, this is certainly the direction that's going to be important in terms of weak coupling and strong coupling and expanding and so on and so on. But if one doesn't do dynamics, if one just looks at the full Hamiltonian, how can one then judge whether it's weak coupling and strong coupling? Does one always have to do dynamics first before one can answer that question, or can one somehow already take some, I don't know, but do you understand what I'm saying?
Yeah, very interesting.
So I agree with Susanna's comment, but this is a dynamical way of mathematically quantifying weak or strong coupling. And the question is, can it also be done statically somehow?
Okay, cool. That's interesting. Thanks. Yeah, so we had lots of questions. I hope I got all of them. I think that's probably it for the questions. So I'd say that's a good point to conclude. So yeah, thanks everyone for tuning in once again. And especially thank you so much to Professor Janet Anders for a really nice talk. Thank you.
Thank you very much, Mark.